we had was that while this planar prediction, right, this planar relationship between the variables is appealing to us in the fact that it is easily explainable, right? We can look at it and we can sort of, in our minds, imagine as the thing changes, this is the output. There's also an advantage of it is that it is relatively actionable, right? If your goal is to try to change this process or achieve optimization in this process, then we can understand how much of which variable to put in order to try to find the upwardmost surface of this particular plane. And it's got the answers on there, right? That way you check and make sure that you got the right answer every time you finish a problem. And I'm like, what is going on here, okay? So the example I used, I talked to them in class about it. I'm like, you overfit. You memorized rather than learning. They are two separate tasks, all right? So learning allows you to be able to generalize the information you have. Memorization makes you a machine. You are an algorithm whenever you memorize, okay? You have no flexibility. You have no ability to adapt. But in this particular case, we'll say the system that is too flexible is memorizing. It's actually adapting too much to the examples and not trying to take into consideration a broader scope. All right, so one of the things we say here is that there's a trade-off between prediction accuracy and interpretability. The more accurate the prediction is relative to any data set that contains a variant characteristic will be a little bit problematic in terms of outcomes. We say linear models are incredibly easy to interpret, whereas things like thin spline models, the ones we were looking at earlier that have deformable surfaces, are actually incredibly hard to interpret because while we understand them from sort of a topological map kind of consideration in 3 dimensions, when we get up into higher dimensionalities, if you can't take them on an individual basis, we don't really understand them. We can't make them strictly systematically applicable. So this, when I say interpretability, that is my ability to take what I have learned from the process of modeling a relationship and then turn it into an actionable system. This is where we talk about the chain of raw information, knowledge, right, and then intelligence. This will make sense to somebody who's been in military space, right? So raw knowledge, intelligence, right? And intelligence becomes systematically actionable, right? And essentially over time, the application of intelligence becomes wisdom, right? That is appropriately applying the knowledge you generate from those spaces. But that paradigm of extraction of useful information and then applying it, pressuring it, leveraging it towards meaningful action required interpretability. I have to be able to interpret the intelligence in order to be able to determine action planning in that particular case. So a good fit versus an overfit or underfit. We were discussing that previously. What is a good fit? A good fit is the one that is Goldilocks fit, right? It's not too hard, not too soft, just right. Not too hot, not too cold, just right. Okay, everybody know the story? Goldilocks and 3 Bears? All right, it's a probably more popular Western fairy tale years around, I'm not sure what you call it. But the idea is, what if you have options between extrema? If you have something that is, let's go with the actual definition of it in cosmology, the Goldilocks zone, right? The orbit of a planet around a star, in order to be able to support life, at least within our solar system, is known to only be able to occur within a very select band or margin away from the sun. Much closer to the sun, it would get too hot and life can't survive. Much further away from the sun, we get too cold and life can't survive, right? So it is the sweet spot between 2 extremes. This is the idea of good fit. A good fit is a model that has enough flexibility to create accurate predictions while a maintained systematic appraisal is required, right, between the trade-offs, good is subjective. The reason why I say good is subjective is because we have to say all other things being equal, the model that provides us with the best results relative to the highest degree of interpretability is likely the best model for our case. Now, what is the reason why I'm saying it in that way? I can deploy a model that has a lot of flexibility, that can create a lot of caveats, a lot of special rules, a lot of considerations, okay? That is what most modern machine learning tools do. Deep learning, advanced deep neural networks, large language model transformers, all that stuff is focused on being generalized, applicable to broad scopes of solution. So in order to do so, it has to be almost completely uninterpretable, all right? So that's what we're talking about whenever we talk about something called parsing. The degree to which a process can be parsed. So think about the idea of parsing a string, cutting it up into chunks, breaking it apart into the elements that are most important. Serial communication is super important to a lot of peripheral interface, so you guys probably have some experience with it. You know, if you don't try to squeeze into the very back row, maybe there would be more room. Everybody wants to sit against the wall. I don't know if I smell bad or if you don't like me to left. I'm not sure, but we've got a lot of back row. Anyway, consideration here is if the model can be deconstructed into relevant subcomponents, then we do have the possibility of creating interpretability from the subcomponents. You can think about the system rather than being a monolithic, enclosed process, a black box, if you will, that has I/O, input and output, right? And we don't know anything that's going on. Parsimonious approach is the one in which we take a lateral slice through the model, and we can see the gears on the inside. We can see how it's working internally in order to be able to sustain operation. Now, just because we can see that does not make the model actionable. It doesn't clarify our approach to the process, but it does improve the potential interpretability of that. Because the more we learn from the model, the more we can act upon it, the better we're going to consider that model with respect to our subjective interpretation of good fit. Now, the reason why I say that that interpretation of good fit is subjective is because it really relies upon all the models that you've tried. You can't try all the models, all right? There are as many potential model implementations as there is data, and even potentially more than that. We'll look at some ways in which we can augment the data in order to be able to look at alternative implementations. So from any given perspective, there are an infinite number of possible models. We're going to select the best we have from those that we are going to try, and we are going to pick the one that seems to be the most useful for us in this particular consideration. While avoiding black box ideology, right? We don't want anything that is completely opaque to our interpretation. Now, this does not necessarily mean opaque to the user or opaque to other individuals. I fully support the idea that a software developer can compartmentalize, they can lock their system behind an API, you can obfuscate the operation of your design. That's not what I'm discussing. What I'm discussing is whether or not you understand how it works. Because I will say today there are probably 90+% of the people that are working in AI have absolutely no idea how the models they actually build work. In truth, they will not be able to tell you the interworkings of it, why this particular function is utilized in this space. They have thrown the spaghetti at the wall, they've seen what sticks, all right? There is a portion of that that makes a kind of weird sense, because when systems get so complex, can we really discreetly describe their elemental components and truly understand and integrate their operation? Probably not. So the more complex, the more systematically comprehensive these systems get, the more difficult it becomes for us to break them down into utilizable chunks that we can carry forward with us. We're going to talk about, this actually talks about the full scope of pretty much all the topics we're going to bring in. Not everything is in here, but it does talk about the range of the flexibility, model flexibility versus interpretability. Now, I don't necessarily think this is 100% true, but this is in fact a subjective chart, right? This is how the author felt about the applications of these technologies. They're pretty close. What we would say is that if I have relatively low flexibility and high interpretability, I would have something like a subset selection space. That is a linear application of only taking into consideration the samples or the feature elements that I'm most interested in from the data set. I can apply very highly refined spatial considerations to those things. Now, why do I say low flexibility? This is a rigid approach, right? I either include the feature or I don't include the feature. Throughout an entire feature, that's rigid, all right? That is very, very hard, that's hardcore. Now, if I say that I want to only take those features that are the most highly correlated to the output, and I want to make my decision based upon those, that is a good approach and relatively easily interpretable, because, think about it this way. If I can tell you what features are the ones that are the most impactful on the output of the system, now I have hooks. I can put my hooks into that element, into that feature, and I can adjust that value as necessary in order to get the desired output. That's everything we want to do within computer science and engineering in general, axiomatically. Measure the thing, right? Improve the thing. That is the desired output. So limiting the scope of the features that you're interested in and finding those that are the critical path to the most important elements is the best way to go about it from a low flexibility standpoint with high explainability, meaning I get a lot out of it in terms of informational capacity. I get a lot of knowledge that I can apply. Next methodology would be least squares regression, right? We understand it to a certain degree, but complexity gets relatively high in multidimensional spaces. Then we use something called generalized additive tree models. We'll just call these trees, or the generic space for trees. We have additive models that do spatial considerations and tree models that function on a flowchart-like basis, right? If-thens type statements, so flow control. Trees are a little primitive from our standpoint, and they can only provide singular binary fusion at each level of operation. So they're relatively easily explainable in the effect that you can dump the decision making of a decision tree into a series of rules that you can read. So many of the rules, the system rules that we use for interpretability of expert systems, which are those systems that are used by clinicians in cancer diagnosis or technicians in running through the troubleshooting page on the back, on the back page of any manual for a device or electronics, is a sort of a flow chart. It's a series of rules based. If this, try this. If then this, try this. That consideration is essentially the tree. Now, generalized additive models are a combination of scope models. What we look at in the GAN space is you can break a solution system down into its component elements. What you do is, instead of sticking with a strictly linear system for all of the variables, you can have a linear system for one, you can have tree system for another, you can have box plotting for another. You can break them apart and treat individual factors as independent models and then additively appraise the whole model from that perspective. The last two are bagging and boosting, right? So we notice that generalized additive models and trees are in here in the mid-flexibility range. They work pretty well. Trees can be applied a couple of different mechanisms here, but what we're gonna talk about, these last two are also trees, okay? Bagging and boosting are types of applications. We'll talk about them with regard to trees. Boosting can be used elsewhere, but bagging is specifically a type of tree operation. And what you end up with is what's called a random forest approach. So you end up with hundreds to thousands of trees. So the interpretability of that system goes to almost nothing, right? It's a forest. You can't make sense of forests. But on an individual level, on an individual basis, each tree is relatively flexible and still relatively interpretable. But on a large global scope, when the system gets a lot of moving parts, its flexibility is very high, but its interpretability is low. All right, so the last one is support vector machines. We're not going to go into those in any detail at the moment, but we will talk about them at a later time. They are highly flexible. They are almost uninterpretable with regard to how they're actually making the decisions. We will see what these look like. I have some new graphics and visualizations for them, but they rely upon a technique called the kernel trick, which is actually a dimensionality up projection, right? Usually everything else we're gonna do up to that point in time is all gonna be dimensionality reduction. We want to cure the curse of dimensionality. Some people actually realize that there is a solution that you can apply, which you project from a lower dimension to a higher dimension, and you're essentially solving a completely different problem. And support vector machines are able to then create surfaces in higher dimensional space that can then be down projected into lower dimensional space. Sound crazy? It is, yes. Right? It is crazy. But there's probably the most, well, this won't be the most advanced technique we have, but I'm going to go ahead and put an additional thing over here on the ultra high flexibility, ultra low interpretability is deep learning, okay? It is incredibly adaptable. There are millions upon millions to billions, right? To actually, there are models out there that are pushing trillion parameter characteristics right now. Trillions of parameters for large language models. Interpret that? No, you can't. You can't make any sense of it. Matter of fact, by the time it gets to, yes?
What's the point in producing something?
They're biomimetic, okay? This is a trillion upon trillion parameter model, okay? This is huge complexity. There is something like 100 million independent neurons just in the prefrontal cortex. So when we think about the interconnectivity between those elements, there is a potential for thousands of synaptic submodels. You, quiet, please. If you don't want to quiet down, you can go out in the hallway. I'm watching you talk, okay? When I'm talking to a student, I expect you to be polite. With that consideration, we have a lot to learn from the brain, okay? But we don't even really know how it works. So what we're doing is we're simulating it. We're creating a model that simulates it, but we're not entirely certain how it's converging to its solutions. I can explain to you that one of the things that's interesting about it is that it is what's called greedy, all right? Meaning that it takes the best solution that it has at the given moment. It doesn't think ahead at the best outputs for the solutions, but it does consider a variety of possibilities at each level. So the training process of large, complex, deep learning systems has to be broken apart into smaller, more achievable, more convergent solutions at the localized level. So all of this decision making sort of, the total is greater than the sum of its parts, right? The whole is greater than what would be considered any individual operation. A random forest, right, bagging and boosting, can massively outperform a single tree to the point to where it's orders of magnitude more than what would be seen as the summation of individual tree performance. That's problematic from a certain perspective because in fact we go, well, how can multiple entities exceed performance, right? Why isn't the individual's performance sort of collective or summational? Well, we actually employ this process within collective discourse. We tend to think that as a group of people, we come to better solutions because we have multiple different perspectives. I think that the same argument can be made for high flexibility models as long as they are wrangled properly, right? You have to get out your chair and your whip like a lion tamer and train it, okay? The reason why is because it's going to cheat. It's going to become aggressive on certain things, and you have to stop it. You have to build rules to slow its process, put guardrails in place, or to be able to learn in an appropriate and adaptive way. So that's a lot of the things that are done at the higher level environments, is trying to figure out how to create spaces where we can control, we can converge the learning of these environments, much like we try to do with organic brain structures. Okay, that clear enough? Okay.
Thank you.
All right, so let's talk about model accuracy assessments. What do we mean when we talk about a model being accurate? There's a lot of different aspects of this paradigm, but one of the key factors here is the necessity of having additional data to appraise the model's overall performance with. Now, where do we get that data from? If anybody answers, we collect more data. No, that is not the correct answer, all right? You have what you have. You got to deal with it. Let me explain to you that can happen. Let's say we set a space probe out into space, and it goes up to an asteroid or something like that. And while it's driving by the asteroid, it's collecting some data, and then all of a sudden it crashes into the asteroid, okay? Collect more data. No.
It should be stored.
Huh?
It should be stored.
Well, what we're actually talking about right now is all offline training. The storage is correct. So when we're thinking about it from the perspective of the data has been collected, all the data we're working with is data that's already happened, right? So if this is real world information, we're not dealing with information that's coming in like on a teletape or over a streaming service, right? This is all locally stored data. We call this offline training because we're able to sort of look forward and back within time in order to be able to create an ideal model that is irrelevant relative to what might be the constraint of a human in that consideration. The constraint of the human in the consideration is that we're only able to make the decision based upon past information that we have stored, but we don't keep all the information. That's an interesting factor. This, even though it is highly complex and has massive storage capacity, it is still not capable of keeping everything that a human experiences throughout life as if it were a camera, right? We're not taking frame by frame shots of life at 60 frames a second at whatever the resolution of the eye is, all right? You can't really do that, right? The brain wouldn't be able to store all that information, and honestly, we wouldn't even be able to recall it. It's too much, too large, and the temporal irregularities would be a huge problem. So what we actually do is we time compress, we interlink elements, and we store representations. Okay, that's the idea. If you don't know what a duck looks like, that's the truth. You don't know what an individual duck looks like. However, your brain has stored the composite of all ducks you've ever seen, and whenever you think about a duck, you're thinking about sort of an idealized representation of your life experience, the summation of all the ducks you've seen, and your model of a duck. You have a model of a duck, and you're building it in your mind. So anytime you see a duck, you just have to put a little pointer, right? Pointer to duck, to the general representation of duck. So that allows you a massive compression with respect to object and spatial orientation. That's divergent, that's a sidetrack, but I like to throw some of those things in there as we're talking about it. So if I say that I'm going to start off with a set of data that was originally prescribed by some process, this could be a survey, it can be sensor data, it can be camera data, it can be pretty much anything, any measurement, metric, digitization, or human input is a prime operational source for this, right? Social media and human behavior can be utilized for mechanisms of attempting to do things like future prediction, right? We talked about the shopping prediction capacity, we talked about the ability to sort of extrapolate out into spaces where we're making recommendations for someone. So that might be what we're ultimately aiming for here. But if we take all of that data, right? We get a data set and we take all of it and we apply it to our model. We show our model all of the answers. what do I have to test the model with? How can I determine whether or not that model is performing well? I've already shown it all the answers. So that means that it's actually already seen it all. If it was inclined to memorize it, and we gave it enough flexibility, right? One of the other things that's interesting about flexibility is it is actually a type of memory. Yes?
Just for the sake of argument, what if you upsample your training data? Isn't that
Are you really creating new data then?
not really, no?
Okay, so you're interpolating. So what would actually happen in that case is you'd have to have a model that would then create new data points, right? So if you think about how you upsample, you are going to either do a localized neighborhood average, right? You're going to average between two samples. That's essentially the same thing as creating a linear model, and then using the linear model to interpolate, and then you're actually assessing the model, the interpolation model's performance based upon your previous assessment, right? You're at your third tier away. Does that make sense?
Yeah.
Okay. I have seen a lot of things about generative data. I've seen a lot of things about modeling data and then utilizing the model to create new data, right? Subsampling, spatial resampling, characteristic temporal resampling, all right? These are all areas you're onto something. When I really like this, I always like to say this. If you think of a question and then you realize there is an area of research that's adjacent to your question, you're doing great because you're alongside of whoever are the contemporary researchers. So you're thinking well. So that's a good perspective to have. So don't be upset if you find out that somebody else has already had your idea. Just recognize that you're on that same wavelength. You could potentially be one step away from making a new discovery that somebody else hasn't thought of. All right. So as long as you're parallel with people who are in the upper space, you're in good company. But the key factor here is that while we can't produce any new data, we can subsample, all right? So we can't really resample, but we can take a sample from the core data. Now what we typically do is we separate these into two groups, training and then testing. Testing is a reserved set of data. I carve it out before I do anything else with the rest of the data. Asterisks, we'll talk about that later. So I carve it out first. It is the first thing that I do before I start my model training. I take it and I set it aside. Now how much do I use? I don't. I really don't. Because there are a variety of different ways to employ this. I could say half and half. That might be good. If you have very little data, that would be terrible. All right? So if your data set is tiny, half and half is not going to work because we don't, curse dimensionality comes in again. N is related to, number of samples is related to the quality of a model being able to adequately predict, adequately interpolate the values for some dimensionality space. So if P is too large, the number of features is too large, and N, the number of samples, is too small, your model is not going to train well and it is not going to generalize well. Meaning that while it may be able to do a relatively decent job on the training data, the data you show it, let's say the first half, when you try and utilize the second half that you set aside to see whether or not it's going to perform, well, you might end up with a totally different set of outcomes, right? The idea here is, well, I can get a good score when I know the answers. That is essentially what's happening. I can get a good score when I know the answers. That's training. But when I don't know the answers and I'm blind to the actual labels, all right, what's the key consideration here? In the training set, we're going to supply them, the model with the targets. Y, the vector Y, will be supplied as part of the data set to the model. It has to be. It's in a supervised learning environment. So within the context specifically of supervised learning, we're talking about the idea of taking a subset, training with it, I give you the answers, all right? And then I test you later on without giving you the answers. I hide this, okay? I'm not actually going to tell you what this performance was as the model, right? I'm just going to look at it, I'm gonna hold it over here, and I'm gonna say, okay, what's the answer to this one? And say, okay, what's the answer to the next one? And along those processes, I will aggregate a score for your performance, okay? The reason why that is, why I have to hide the performance from the testing environment, is if I tell it whether it got it right or wrong, even just telling it whether it got it right or wrong might actually influence that outcome. It can't bias the system, right? So this has to be completely, we call this a validation type approach, right? We validate the assessment of the model. There are a couple of different tiers of validation and a couple of different ways to break this apart, but validation within regression frameworks, we validate by the training and testing approach. So systematically, we can read these fairly easily. The subnotation training, the mean squared error of training is supplied by the average of I elements that are members of a set training, right? Training set is what I'm going to refer to here. That is all the samples that I have taken from the original training data. Now this includes all features. I haven't done anything with reducing the features yet. I've just sorted specific individuals out of that set to act as my new process. Think about this a bit like polling, okay? This room is a subset of the college. I could take a subset of you, right? I could break you in half, and then I could provide a survey to one group and a survey to another group. And I could assess the differences between those subgroups. I could say that maybe the differences between those subgroups is actually representational based upon the sliver or the slice of the college that is represented here. So the characteristic here is that if I built a model of the whole college based upon some group of you, let's say a more relatively useful example would be the example of what is often provided, which is either 80-20 or 70-30. 70-30 is considered to be kind of the gold standard when it comes to traditional machine learning. 70% is applied to training, 30% is applied to testing, or reserved for testing. We often say reserved for testing. Now, placing those values in reserve means that they're untouched, they're they're employed in any aspect of the training process or any other feature selection extraction methodology at this level. So the set of examples in testing and the set of examples in training, right, training examples here, will be separated from one another as to what is applied to the system. Everybody get that? Okay. The difference between these systems allows us to assess a couple of things that are relatively useful for us even during the process of training, right? We don't have to wait for the model to be completely done learning in order for us to get something useful out of the training or the testing performance, right? So the training is learning from the training, and then we're evaluating it based upon the testing. In this example, we have a true underlying system. So black curve is true, ground truth in this space. So this curve up here is, I'm going to blow it up a little bit so we can see it a little bit clearer, because sometimes these aren't great unless you see them at a little higher resolution. This black curvature is actually the generative function. Now why I say it's a generative function is because this is synthetic data. I start off with a known f of x function, and then I build the data points by randomly inputting values into x and then adding some noise characteristics to it, some zero mean Gaussian noise, right? This simulates the same process as randomly selecting a sample from a function, a natural process that has that distribution. Why am I talking about this? Because a lot of the examples in the book are not real data, all right? They're toy data, they're simulated data that we use to explain the underlying processes. It actually makes it a lot more stable because of the fact that we can know what the true function is. Otherwise, if this was real data, could I ever plot that black line?
No.
No, I can't. So without knowing that, then I don't really have anything to truly compare it to. So by creating synthetic data, I can provide you with a theoretical ground truth. All right, so black is a theoretical ground truth. And blue and and green here are both versions, as well as yellow, right? So yellow is the linear version. Blue is some form of a complex quadratic, I believe either like a square, cube, or something like that. Not even higher dimensionality, but probably right around the line of like a second or third order system. And then the green one is crazy flexible, all right? High order, multiple different abilities, all right? So anytime that I take a higher order version of a subfeature in dimensional space, what does it allow me to do? It allows me to change the direction of the graph, right? Square, cube, whatever else. I can change my direction on an instantaneous whim. So black is the actual line, green is the one that I have tried to find as the ideal surface. What happened to green? What did it start to do? It tried to push itself to where it was close to specific examples, or clusters of specific examples. We said the reason why they are distant from the actual black line is because what? We induced artificial variance as a result of implementing Gaussian noise. We put noise in to simulate real world noise, and so it's fitting to what? Noise. It's no longer fitting to just the data model, it's now fitting to data model plus noise. It's fitting to reducible plus irreducible. So when we try to overfit, we end up with these crazy little junts and jaunts because it has to try to jump around to compensate for the noise that was input in the original signal. Now blue is satisfaction that comes relatively close to the underlying ground truth because of the fact that it is just flexible enough to be able to fit. What about the linear model? This is not a linear system, right? Strictly, we can tell right off the bat by even a simple increase in flexibility to a second or third order system that the first order linear system is going to be incapable of totally making its determination. Now, let's look at what's happening over here. Note the colors of these little dot points, and notice the horizontal axis of this graph. Flexibility is on the horizontal axis. As I increase the flexibility, what am I doing? I am changing the function that I'm utilizing as my f hat, right? So f hat increases in dimensionality by adding additional factors, additional beta coefficients, and additional higher order elements, right? Cubes, squares, fourth, fifth order elements to compensate for the values as they change shape and direction. So the equation is just going to get longer and longer. As I said beforehand, those coefficients are a bit like storage areas. They're like memory storage. We can adjust them. They are modeling the underlying system. So initially we start off with a first order system, right? It's actually even down here below too. That is our linear system. Now the reason why I say it's at 2 is what? Beta naught, the biasing coefficient, is actually counts, right? So it technically does have 2 parameters that are adjustable. So the bias parameter is adjustable and the slope parameter is adjustable. So the intercept and slope are adjustable. So it's technically considered a 2 in terms of which portions are flexible, which portions can you change. Go up to the 5th order system, or right around the 5th order system, which is 4 adjustable parameters, which is right around what I thought it was going to be, like 3rd or 4th order. 4 elements, and then a biasing term, right, or intercept coefficient. What does that correspond with? The first one is the linear, right? We said that one's garbage. What are we measuring over here on this side? This is MSE, that is the mean squared error. Notice there are 2 lines. What are we corresponding with here? It says the curve on the right is the MSE of testing. Gray curve is MSE training. Now, what happens after the blue line? Training is at the bottom, testing is at the top, right? Yeah, you pointed out the thing that I think is the most important. A characteristic divergence in performance. They diverge from one another at that point in time. That divergence is the set point, the critical point of the balance value between two systems, right? The bias and the variance as it relates to the underlying environment. The system becomes more biased towards the values within the training set and starts memorizing. So past that point, we start memorizing. What ends up happening? The testing, the evaluation set, increases in error after that point. The reason why is because of the fact that it is now making changes for, it is adjusting to data set specific characteristics, right? And since the training set is a separate set from the testing set, it's actually going to abuse knowledge of the training set to make rules specific implementations, right? It's going to abuse its flexibility to memorize training examples. Thus, whenever I attempt to apply or to generalize the values of the coefficients that have been learned from the training data to the testing data, I'm going to find that the testing data is actually even lower than it was beforehand, right? The error actually goes back up. So for a while, the error is together, right? They're both moving in the same direction. We say that at that point in time is generalizable because the things we're learning from training are applicable to testing. But after a certain point of flexibility, once we've hit the ideal functional approximation, anything that we do to increase the flexibility past that point is actually in error and will cause the testing performance, the generalizability of the model to diverge and cause the testing to reveal that while performance is increasing, right, so the accuracy is still getting better, it's not getting better for everybody. And especially, it will not get better for potential future instances. Testing is a bit like the concept of going and getting new data. It's our way in which we simulate the process of new sample collection. All right, thank you guys. I'll see you on Friday. As always, any questions? I'll wait a minute in case anybody has anything.
So my question is, if the green, what is the green line? What algorithm we are using? Yeah. So if we are training those, we have flexibility, right? We are having more flexibility for green curve. It's for the training for flexibility. But for testing, it goes up. Like we are not, we are getting more error. So that is the case.
Let's think about that. That's the key thing I want you to think about. Why is the testing error? What's the training error being out of the testing error?
Because of the excess noises, they are produced.
Is green version of this line closer to the underlying depth model, the black line, or is the blue line closer?
Blue line.
So think about it from the perspective of likelihood, probability, density function placed upon that line through the length of it. How likely is the sample from training and testing to fall on top of the black line?
It's almost
Much more likely
to fall.
narrower band around the black line than it is to fall within the band of the green line.
Yeah.
Because the green line now has a margin around the outside of it, in which values will fall very. So if the values of the estimate fall outside or far away from the actual likelihood, since the data set that these were sourced from has the same distribution, the testing data has the same distribution as the training data. Right, or should have
Approximate.
other things we rely on.
So
Subject should have a mild version in its characteristics, right? Relative to
Well, I'm not saying that I want you to like commend me or something like that.
so it's like the model you said, barging model. I can assume this is the green line. The random forest model. Those are first one is the linear, right?
Right.
Linear. Then so I'm talking about the model. So what kind of model we can expect from the green line?
That is a 26 22nd dimensional model.
Oh.
22nd to 23rd dimensional, I'm
Okay.
extrapolating. But you can look and you can see the flexibility goes up. So this blue is 5th dimensional, this is 20, so we're at 22nd,
Oh,
23rd
20,
dimensionality,
23rd
right?
dimension.
So by the time we get up to that level,
Oh.
we have 20.
We have too much features
How many
and
beta parameters do we have? We have 23
20
beta
beta
parameters,
parameters.
right? From beta naught up to beta 22.
parameters. So parameter increases, as a result we getting
That's
more
flexibility.
flexibility.
So the increase
Oh.
in parameterization is the increase in flexibility.
Flexibility.
That
That's-
allows the surface. So what is flexibility? Flexibility is the ability to instantaneously change direction, right? So over the axis of this surface, it's flexible
Flexible.
because of the fact that it has the ability to conform to the
Conform.
surface. It's the reason why I say it's like a wet paper towel whenever it's at really
Yes.
high dimensionality, because it just flop. I say that the model takes the shape of its container at high flexibility. It literally is like water. You pour it in and it just takes up the shape of its container.
Okay, thank you.
I always do this weird asymmetry. I never know how long any given lecture is going to take. Never.